Hello everyone. Hope you're all fine. And I haven't seen you for 2 weeks, around 2 weeks. And we had two lectures last week, and we had it off due to the coronavirus attacking the whole globe. In the previous lecture, we study the Pearson correlation coefficient and its hypothesis testing. Remember that we had it was the correlation analysis, and so the correlation coefficient for the Pearson is exactly the same as the other correlation coefficients. There are so many correlation coefficients that appear in the literature, but today's correlation coefficient is a very well-known coefficient. It is mostly used correlation coefficient. It's called the Spearman's coefficient, or maybe it's called the Spearman-Rank correlation coefficient. The idea behind the Spearman correlation coefficient is to rank the X and Y observations separately and compute the Pearson correlation coefficient on the ranks rather than on the original data. So let me write you this as probably a good definition of the Spearman rank correlation. So the Spearman's correlation coefficient. Normally we have it with a letter R, and we have a subscript as S to distinguish between the Pearson and the Spearman rank correlation. Let me write you the definition. It's a good definition for the Spearman. The idea behind this correlation, the idea behind this coefficient is to rank the X and Y observations separately and compute the Pearson correlation coefficient on the ranks rather than the original data. If you already know how to calculate the Pearson correlation coefficient, reading this definition, you should be able to get the Spearman correlation coefficient. What you do basically, you have an X and Y variable, and you need to rank the X and Y from coding ranking. You should have the coding from 1. The smallest value is coded as 1, and the highest value is coded as n. Think that the sample size is n. So of course, the value of the Spearman correlation is usually different from the value of the Pearson are calculated on the original data. But for large sample sizes, the two values are usually relatively close. So you may think that why bother with ranks? Well, if there are no ties among the x and axis and no ties among the y, then the Spearman correlation can be computed much more simply than Pearson correlation using the following formula. There is a formula for the Spearman, which is much easier than the Pearson correlation, which is RS equals 1 minus 6 times the sum of di square. So I'm gonna shorten the division, and that's divided by n times n square minus 1. If your measurements for both an x and y having decimal places, the calculation of the Pearson correlation without using computing facility computer, and it's very hard. The calculation is hard. But if using the Spearman correlation, rank correlation, is much easier because you're ranking and you'll have every value will be integer starting from 1 ending to n for x and y, and di is the difference. So the difference, the calculation is pretty simple. So where di equals the rank xi minus the rank yi, that's the difference. So n is the sample size, of course. So this is usually used when there is no when there is no ties. This formula is valid when there is no ties. So what we mean by ties, if you're not having equal measurements of for any values of x or any value of y's, so it means the ranking will be different, all different. You shouldn't have similar ranking. For similar ranking, you're not able to use this to get the Spearman correlation. So what you do is you're gonna use, for the ranking, you're gonna use the Pearson correlation coefficient formula to get the Spearman rank correlation. So this is a good formula, an easy formula to get the Spearman rank correlation. We have the similar hypothesis we had in here. I'm gonna place it. So this is remember from the previous lecture. I'm gonna copy these lecture notes in here. Gonna have it downward. My lecture note. Copy this. So let's have it in here. I'm gonna like it here. It seems that it doesn't fit here. I'm gonna resize it. So this is from the previous lecture. If there is a ties, so once you complete ranking, use the Pearson correlation coefficient. If there is a tie, use the ranking. Have the you should use this formula. If there is a tie, if there is a tie, use this for ranking values. You're not using the original data set, you should use the ranking. And the hypothesis, we have the same. We use the same hypothesis. We have same hypothesis to test. And we use the same statistics, of course. Use the same statistics with the same degree of freedom. Degree of freedom. Okay. To clarify the calculation of the Spearman rank correlation, let's have an example, get an example. I have an example in the book I'm using for this course. Let me get this. Okay, so this is a good example, 10.8. I'm gonna place it to you in your lecture notes. You're gonna have it, your lecture notes. Let's study these examples. I found it a good one. Copy here. Go back to my lecture note. Place it right here. Okay, this is the example. Gonna enlarge it. Okay. This is the example. Gonna have it larger, a bit larger. So let me read you the example. Okay. A study by Mosh and Hay examined relative age effects in soccer in various northern and southern hemisphere countries. For each country, a sample consisting of all players in the highest professional soccer league was investigated. The data for Germany are given below. A cutoff date of August 1 applies in Germany. Since participation of cutoff dates vary by country, foreign players were excluded from their analysis. For each country, the distribution of professional players' birthdays was computed by month. This birthday distribution were then compared with that of the general population of that country. The first column is the month after the cutoff date in which the player was born. The second column is the number of professional soccer players born in the respective months of the competition year. The third column is the number of soccer players that would be expected on the basis of official birth statistics, assuming that the birth distribution of soccer professionals is the same as that of general population and that no relative age exists. The fourth column is the difference between the expected and the observed number of players. So the question is, is there any association between the month and the difference? So the hypothesis we can construct for this would be HO equals no correlation, and the alternative is rho is not equal to null. That's the hypothesis we construct, and let's build up with an error probability as 0.05. Consider the universal error probability. So the months are already in ranking position, so no need to rank the months. So let's have the months, assign it as xi. This is the rank equals to its value. And the difference, we are dealing with the difference, so we need to get this is the yi, and the ranking yi, let's construct that. The smallest value should have the value 1. So think this is minus 7.71 is the smallest one, so I'm gonna place the ranking as 1. And this second smallest value should be 6.83. So this is going to get the value is 2. And the third smallest value is minus 6.16. This is going to be 3. And let's see. And the next one is minus 3.38. And this is should be in the number position 4. And minus 3.27 is going to be 5. Minus 2.60 is going to be 6. This one is 6. And the next smallest should be minus 0.93. That is going to be 7. And the next smallest will be minus 0.16. This is in the position of 8, ranking 8. And the next smallest will be no negative value anymore. So we're going to use 2.95 will be in the 9th position. And the next one, this is going to be 10, 5.62, and 8.73 becomes 11 in the 11th position. And 13.74 is the highest value will go, the ranking will be 12. So the sample size is 12 and the largest ranking will be 12. Okay, so the xi, so this is the xi value, and the ranking of xi are also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. No difference. So the calculation will be pretty simple. Okay, if you have, so you need to get the difference. I'm gonna place the difference in here. I have a space here. So subtracting from 1 to 11, you get minus 10. So 1 minus 11 becomes minus 10. And 2 minus 10 becomes minus 8. The difference, you need all this difference. And 3 minus 12 becomes minus 9. 4 minus 6 becomes minus 2. And I'm gonna keep going the rest. So the next one will be minus 3, another minus 3, 3, 6, 6, 9, 4, and 7. Okay, now I can easily get the Spearman rank correlation. I'm gonna copy the formula. You may not remember the formula. I'm gonna get it for you. That's the formula we use for the Spearman rank correlation. Place it here, right here. That's okay. Let's move it downward a bit. Gonna delete this. Okay, the calculation is not that hard. So you have 1 minus you have minus 10 squared. The first value is minus 10. The first difference, ranking difference, is minus 10, and square it plus minus 8 square plus minus 9 square plus minus 2 square plus minus 3 square plus minus 3 square plus 3 square plus 6 square plus another 6 square plus 9 square plus 4 square plus 7 square. Large the division part, and that's divided by 12 times 12 square minus 1. The sample size is 12, and probably I should resize this to fit it. Okay, gonna enlarge it here. Okay. I have 7 square here. 7 square. Okay, this calculation seems to be easy to when compared to the Pearson correlation coefficient. It's much easier to calculate, and if you perform this calculation yourself, you'll see that the Spearman rank correlation will be minus 0.727. That's the Spearman rank correlation. Okay. Okay. That's the result for the Spearman correlation. Delete this. Okay. Okay, seems to be a negative correlation. An increment in the month will result in decrement and the difference. That's what the interpretation. The interpretation is very much similar to the Pearson ranking, the Pearson correlation coefficient. There are some other correlation coefficient in the literature. Since we're running out of time for this lecture, this committee, we don't have a lecture in committee in 4. I'm not able to lecture you the other correlation coefficient, but I can tell you the name of those type of correlation coefficient. And this type of correlation coefficient are usually called non-parametric correlation coefficient. And this is the most well-known non-parametric correlation coefficient called the Spearman. And the others you may come across when you study SPSS in your project. Probably you will use SPSS or some other statistical software. Kendall's Tau B, Kendall's Tau C, and Kruskal Gamma are the most well-known correlation coefficient for ranking variables. If you are not suspecting from X and Y, they are both distributed normally, you're not expected to use the ranking correlations, any ranking correlations, Spearman or other correlation. You should definitely use the Pearson correlation coefficient to get the measurement of the relationship. Okay, let's see whether this correlation coefficient is significantly different from 0. The testing the hypothesis is exactly the same. We use the same statistic, T statistics. This is the calculated statistics, rho x and y minus rho null divided by the standard error of the correlation coefficient. So in this case, the calculated statistic is in place of rho x and y, we have rho s. So the calculated statistics I'm going to use, let's have the calculated statistics equals rho s minus rho null, that's divided by the standard error of the correlation coefficient. The standard error is exactly the same. So the standard error of the correlation coefficient for the Spearman is identical to the Pearson correlation coefficient. So no difference. So you have within the square root 1 minus the Spearman correlation coefficient square, and that's divided by n minus 2. That's how you get the standard error of the Spearman correlation. The calculated statistics, let's get this value, the t-calc equals minus 0.7 to 7 minus 0. The row null within the see that this is 0. Since it's 0, this is row null, that is 0, and that's divided by the standard error. So I'm gonna write it directly, no calculation for this Spearman ranking correlation. So this is going to be 1 minus 0.727 square. Since it is a square, taking the positive and negative, no difference, will make no difference, and that's divided by 12 minus 2. Okay, the calculated statistics. I'm gonna perform this this statistics. I'm gonna use my calculator. Give me 20 seconds to get this for you. Okay. Okay, minus 0.727 divided by the square root 1 minus 727 square divided by 10. This is, according to my calculation, is minus 3.348. So approximately this is. So I already drawn a picture of for showing you the critical region. So since this is a double-sided hypothesis, I'm gonna have sorry about that. Okay, let's get it smaller of this picture. Move it a bit on the top of the page. So I have two rejection region, and I'm gonna split the rejection part on the right hand side, which is going to be 0.025. This is 20. Okay, delete this. Gonna have 25. I'm gonna have another rejection part on the left hand side. So this is going to be, and I have another one here checked. This is going to be 0.025. So the accept region will be 0.95, and the critical value, since the degree of freedom is n minus 2, the degree of freedom is n minus 2, becomes 12 minus 2 is 10. So I need to get the critical value to be 10, 0.025. Okay. I already have a table, student T distribution table. The degree of freedom is going to be 10. Let's have it read. Okay, 10. So I'm gonna pick up this row. I'm interested in this row. Okay, the column 0.025. That's the column I'm interested. So this is the column I'm interested. Okay, and the value I need to get is 0. Sorry about that. Okay, that's the value, 2.228. Okay, the critical value is 2.228. So the left hand side will be minus 2.228, and right hand side I have 2.228. Okay, the calculated statistics was 3, 4. I made a mistake in here. 3, 4, 8. It will clearly, this is going to fall within the rejection part of the right hand side of the graphical representation. So I'm gonna have a representation of the value. Okay, so the critical value is minus 3, 3, 4, 8. Okay, it is falling within the rejection region, so I'm gonna okay, I want to highlight the rejection region, paint color the rejection part. I always do that. Okay, I have another one in here. I would like to also highlight okay. Since minus 3.348 is falling within the rejection region, we reject the null hypothesis with alpha 0.05 level of significance. You can also construct the confidence interval. I am not expecting the confidence interval to include I'm sorry, the calculated statistics should fall on the left hand side. I made a mistake. I'm sorry about that. So this is a negative value. It should fall within the rejection region. I'm going to place it here. This is minus 3.348. Delete this. Sorry about that. Within the rejection region, we reject the null hypothesis. So the construction of the confidence interval is similar to the other test statistics. So the confidence interval simply is calculated by the Spearman rank correlation minus the critical value, T critical times, you should have the standard error of the Spearman rank correlation that is less than the actual correlation, less equal to Spearman ranking correlation RS plus T critical times the standard error of the ranking correlation. So in this case, let's get this. We know already the Spearman ranking correlation is minus 0.727 minus, and the critical value is 2.228, and the standard error, I need to get it calculated for you. Use a calculator. This is 0.217 rho is equal minus 0.727. This time we have plus in here, 2.228 times 0.217. Clearly that the lower bound is going to be negative and the upper bound is going to be negative. The zero value will not be included in the confidence interval because we rejected the null hypothesis for the double-sided. So if you get this calculation done, let's see, I'm gonna do it for you. Equals the lower bound is minus 1.21 rho less equal, and the upper bound is going to be also negative minus 0.244. Notice that the lower bound is minus 1.21, which is in practice, this is not observable. The correlation coefficient can be, the minimum value of the correlation coefficient is going to be minus 1. So I'm going to modify this. This can't be minus 1.21. So I'm going to modify it as minus 1 rho equal minus less equal 0.244. So this is the confidence interval for the Spearman ranking correlation, or the actual correlation coefficient. So you need to modify this in this way. So if you have this type of confidence interval, this is incorrect, incorrect, modified. So if the upper bound is greater than plus 1, and you should avoid the large number, have it, the upper bound cannot exceed 1 and the lower bound can never be less than minus 1. So this is the true confidence interval. Correct confidence. Okay. Before I end up the lecture, I'd like you to have to study yourself an exercise for practice. Let me see. In the book, I should have some exercises. Okay, this is a good exercise for this problem. Number 2, I'm gonna leave it for you. Study yourself. Okay. I'm gonna go back to my lecture notes. Nudge it for you. So this is the homework. You study yourself. Okay. This is a homework. Okay. I hope you enjoyed the lecture. I'm ending here the lecture, and I have one more lecture tomorrow. I'm going to prepare the lecture notes, repeating all the courses for the committee 3. Tomorrow you will have it, and I'm gonna share this on YouTube. Place a link within our university feature of distance teaching, so you will get the link to watch this video. And I wish you a very good luck in the examination. Of course, you'll have one more lecture tomorrow related to the examination. And take care of yourself and have a great rest. Bye.